Okay, so this is section 16.3, video 3. This will be our last video for this section. And this is pretty much just all examples based upon the fact that now we know that the test for something being conservative is going to be that dp dy equals dq dx. So the biggest thing is to define those things. Okay, so it says the figure shows the vector field f as 2xy x squared and three curves that start at 1, 2 and end at 3, 2. Explain why the line integral f dot dr has the same value for all three curves. Well, if it's got the same value for all three curves, that means it has to be independent of path, which means it has to be conservative. So basically, you're starting here and we're ending here. And it doesn't make any difference whether we go on this path. Wow, that one was harder to trace over than I thought it would. Or if we go this direction. Or if we go this direction. We are starting and ending at exactly the same point. So why does it not matter? Well, it won't matter as long as it's conservative and independent of path. And the way we can test that now, so for part A, the way we can test that now, again, is to find dp dy and see if that equals dq dx. So we'll put a question mark. That's our question. Okay, so the biggest thing is to remember now what the force, that this is P, this is Q. Okay, it's the first function is P. It just goes alphabetical, P and then Q. The first component is your P. The second component is your Q. So what is the derivative of P with respect to Y? Well, the partial derivative of P with respect to Y is going to be 2x. Then what is the derivative of Q with respect to X? The partial derivative of Q with respect to X also happens to be 2x. So since dp dy equals dq dx, this is conservative, which implies independent of path. So that's why the line integral will not make any difference which one of those three curves we follow. Okay. And because this is conservative and independent of path, that means that the gradient is defined as that capital F. So for part B, we know that capital F is the gradient, because that's what it means to be conservative and independent of path. So we can guarantee that fact. So let's go ahead and take a look at this. I'm going to scroll back up and down until I get the stuff written down here. So f sub x is 2xy. So f sub x is 2xy. So the antiderivative with respect to x is going to be x squared y plus some other function of y. F sub y here is defined to be x squared. So f sub y is x squared. Taking f sub y from our f function that we found, that's going to give us x squared plus g prime of y. Okay, the fact that those two things are the same means that g prime of y is 0, or the antiderivative, g of y, is some constant k. Ultimately, that's not going to matter because we're going to ultimately put this into the fundamental theorem, but it's still important to find that part just in case your g of y is something other than just a constant. So our function of xy here is x squared y plus k. Well, because it is independent of path, we know that the line integral of f dot dr is f of xy, which in this case is x squared y, evaluated at our endpoints. Now, I think they actually gave them to us here. Yeah, 1, 2, and 3, 2. So we started at 1, 2, and we finished at 3, 2. So we'll plug that stuff in. So let's see, if we plug in 3 for x, that's 9 times 2 is 18, minus, plugging a 1 in for x, that's 1 times 2 is 2. So we get 16. And that's it. All right, so let's go ahead and move on to the next one, because the next one's going to be, oh, actually, it's not the next one, it's the one after that, but next one won't be too bad. If you notice there's not a lot of space, that should probably give you a little bit of a hint. Determine whether or not f is a conservative vector field. If it is, find a function f such that capital F equals gradient of f. Okay, the way we're going to determine this is to find dp dy and dq dx. So remember, define this as your p, that as your q. So it's dp dy. So dp dy, the derivative of p with respect to y. Well, the derivative of e to the y is still just e to the y, so it's x e to the y. The derivative of q with respect to x, again, derivative of e to the x is e to the x, so that's going to be y e to the x. These two things do not equal each other. dp dy is not equal to dq dx, which means not conservative. Which means if you were actually trying to take a line integral, you would have to do it the old-fashioned way of taking a line integral, because the path that you follow would actually matter. So not conservative. We cannot write capital F as the gradient of lowercase f. Okay, and that's the easy test. All right, number 6. Number 6 is a bit more involved. So it says, find a function f such that f equals the gradient of f. So in this case, it's telling you to find a function f such that the capital F is the gradient of f. That is implying conservative, because they're telling us that this is the case. It won't tell you to find it if you can't find it. It would say verify or something, but this part right here implies conservative. So we have to be able to do it. And then use part A to evaluate the line integral f dot dr along the given curve. And the reason that this is important, that this implies this, is because this is a three-dimensional vector. So we've got 3 variables. So when we do this, we're going to have 3 variables. And I'm going to try and put our new concepts in this color of blue here to make sure that you see, because there's going to be a bit of things that are going to be slightly different since we haven't dealt with the 3 variable thing before. The general idea starts off the same way. So part A, we still want to find lowercase f. Well, if we are assuming that capital F's vector field is defined to be the gradient, that means that f sub x is the component of x and the force, which is yz. So then if I take the antiderivative with respect to x, I'm going to get x yz plus, now here is one of the new things. This, whatever this constant is out to the right here, does not just have to be some function of y, it could also be a function of z. So whatever this is a function of y and z, or could be a function of y and z. Because either one of those two things, when you take the derivative, is going to go to 0. So that's a new concept. We're going to go back to green because the rest of this is going to, well, at least initially, is going to be the same idea. So fy, well, that's this piece, that's xz. And then if I was to take the derivative, of the original function with respect to y. Let's see, that's going to give us, taking the derivative of the first part with respect to y as xz, plus, and I'm only going to do part of this in blue. This will be g sub y of yz. So that part is a slightly new concept. And these two things are the same. Xz matches up, so that tells me that g sub y of yz has to equal 0. Well, that means that the antiderivative with respect to y is going to be some function of yz, and that's going to equal a constant, but the constant could also be a function of z. So this piece right here could be any function of z, because when you take the derivative of that, once again, with respect to y, the z part is going to go away. So that's a new concept. Now we're going to kind of put that stuff back together. So we'll say that's not really a new concept, so we'll go therefore f so far, because we haven't finished it, f is going to be x, y, z, plus our g of yz, which right now is h of z. But we have another component on this one. So if that is f of xy, f is going to be xyz, so let's write this over here. So f so far is going to equal x, y, z plus h of z. But we know, and this is all new at this point, that f sub z is this piece, xy plus 2z. Now, taking the derivative of this with respect to z now, because I'm trying to match the z part, is going to give us f sub z is, let's see, the derivative of xyz is going to be xy. That's good, that matches, plus some h prime of z. So then this stuff has to match. The xy's match, so what that means is that 2z is h prime of z. Now that's all functions of z, so when I take the antiderivative, h of z is going to equal, let's see, that's going to be the antiderivative of 2z is going to be z squared plus k. So after all of this, and I don't want to say finally, but at least we get to our our f. So finally we get f, which is x, y, z, plus our h of z, which is z squared plus k. So that's the original function that this one comes from. And you could double check, take the partial of x, y, z plus z squared plus k with respect to x, with respect to y, with respect to z, and you should get back to your vector field. But that's not really what the question is asking us. It really wants us to evaluate this over the line segment 1, 0, negative 2 to 4, 6, 3. So we're going to use our fundamental theorem, which says for part B, the line integral of f dot dr, because we know this is a conservative vector field, is going to be the function xyz plus z squared. Again, we don't need the k part because it's going to go away, from 1, 0, negative 2 to 4, 6, 3. All right, so plugging that in, 4 times 6 times 3, what's that going to be? 24 times 3 is 72, plus z squared, which is 9 more, so that's 81, minus Plugging in 1, 0, and -2. The first part x, y, z is 0, and then z squared is 4, so -4. So it looks like we get 77 out of this. And there's your line integral. All right, these problems do take a bit of time, especially one that's got three pieces to it like that. All right, so let's move on to the next example. Show that the line integral is independent of path and evaluate the line integral. So I'm going to use a little bit more intuition on this one, but we're still going to do the basics. So showing that it's independent of path, we need to find dp dy, which is, see, the derivative of p with respect to y. P is tangent of y, so that's going to be secant squared y. We need to find dq dx. Q is x secant squared y. Taking the derivative of that with respect to x gets rid of the x, so that is secant squared y. Those two things equal each other, so we are good. We have shown that it is independent of path, which means conservative. So independent of path implies conservative, which means that we can define the gradient as tangent y x secant squared y. All right, so you could go through the entire process. This is where I'm going to tell you, use a little intuition. If you can't go through the entire process, I'm only doing this to save time. Once you go through that entire process, you're going to get that f is x tangent of y plus k. So again, use a little intuition or go through the entire process. I'm just saving us a little time. So that means that the line integral of f dot dr is going to be x tangent of y evaluated from, and again, it gives us nice points here, 1, 0 to 2 pi fourths. So plugging in a pi fourths for y is going to give us tangent of pi fourths is 1 times 2 is 2. Tangent of 0 is 0, so 2 minus 0 is 2. Okay, and again, hopefully you can do this part again by using a little bit of intuition. If you were to take the antiderivative of tangent y with respect to x, you would get the x tangent of y. Taking the derivative of that, you would get x secant squared of y, so that would match what you have on the other side. So your derivative with respect to y would equal 0, so the antiderivative would be k. If you can't think of that like using intuition, again, just write it all out. All right, find the work done, which is the line integral, by the force field F in a moving object from P to Q. So from one point to the other. So again, first thing we want to check is this conservative? If not, we have to go back to 7.2 and do the long line integral, which is probably more difficult. So let's see, dp dy is going to be, with respect to y, that's going to be 3y to the 1/2. dq dx, the derivative of that part with respect to x is going to be 3 square root of y. Those two things are the same. So we are good. It's conservative. So that means that we can do f, and again, I'm going to go off a little bit of intuition here. F is going to end up being, let's see, so the antiderivative, so it's going to be 2xy to the 3/2. If you took the derivative of that thing with respect to y, you would get the 3y square root of y. So again, which is going to be plus k. All right. And then we're going to use the fact that this is conservative. So the work done is going to be the line integral of f dot dr, which is going to be 2xy to the 3/2 evaluated from 1, 1 to 2, 4. See, plugging in a 2 for x, we're going to get 4 times 4 to the 3/2 power. That's 8. So 4 times 8 is 32. Minus, plugging in a 1, we're going to get 2 times 1 times 1, which is 2. So we should get 30. All right, and I'm sorry if I went a little bit faster, but again, this video is running a little bit long. But those are the last 2 actual examples. So the only other thing I want to do is on this last page here, I want to kind of give you a quick summary of everything that we've done. So let's do a summary. All right, so the summary, let F equal some kind of a vector field which is defined as P of xy I plus Q of xy j. The first thing that we need to remember is 1, if the partial of P with respect to y equals the partial of Q with respect to x, then F is conservative. Okay, feeding off of that one, if F is conservative, F then equals the gradient of lowercase f. Okay, and still yet off of those, if F is conservative, then that means that the line integral of f dot dr is independent of path. It makes no difference which way we take to get from one endpoint to the other. Okay, the fourth thing, we only have 5 of them. If F is conservative, then the line integral of f dot dr is the same thing as the function of r of b minus the function of r of a. And we'll just add this in there where r of b and r of a are the endpoints of C, of your curve that this is over top of. Okay, fundamental theorem of line integrals right there. And then the last one. If F equals P of xyz plus Q of xyz plus, and we use R, oops, I forgot, there's an I here, J here, got to put it in vector form, R of x, y, z, it's a capital R, K. So now this is 3-dimensional. We have no efficient way of determining if lowercase f is conservative. So we did that one when we did the 3-dimensional one, but it told us that it was going that capital F equals the gradient, which implies conservative. If we are just given this vector field, we have no efficient way of determining whether F is conservative unless they tell it to us yet. It's coming. All right, that's plenty enough for these videos. You should have plenty enough to get the work done, so should be good.